Hi everyone, thanks for coming. My name's Yuan. I'm an applied data scientist at Microsoft in the cloud and AI, in the AI framework team. Today I would like to introduce you this Nimbus ML package. So fortunately or unfortunately, the original speaker was on parental leave. So I'm pretty sure he's quite occupied and cannot attend this talk today. So this will be the very first talk of Microsoft about Nimbus ML in the external side at any conferences. And we are going to have another talk about Nimbus ML and ML.NET in this year's KDD in Alaska. So if you are also interested or you are attending that conference, you will definitely get a lot more technical details about ML.NET or Nimbus ML there. So today, hopefully, I will cover most of the high-level concepts and the important design ideas we have in this machine learning package to all of you and deliver all the useful messages. So without further ado, let's get started. What is Nimbus ML? So Nimbus is actually, I'm pretty sure it's coming from what they have in Harry Potter's movie, the Groom. It's definitely not because Microsoft like Azure, like cloud, we name everything, something relates to cloud. It's because we like Harry Potter. And also, I want to emphasize that we do share two common points with this Nimbus. I think it's 2001. And the first thing is we are very fast. So you can imagine Harry Potter rides, he fly everywhere, he wins the whatever championship, I don't know the name because it's very fast. So we are very, very fast. We can claim that we are 5 to 100 times faster than Scikit-learn, which is one of the most popular machine learning package in Python. First, we are fast, and second, the common things we can use it to sweep. Anybody know sweep? You like sweeping the floor? So use Nimbus ML, you can actually do parameter sweeping. So for many of you, you might know there are tons of parameters in a machine learning package you can specify. For instance, you are learning a random forest, you are learning a decision tree. There are so many hyperparameters you can test out. You can specify, I want to learn with 100 leaves, I want to learn with 300 features. So there are so many parameters you need to specify. So using Nimbus ML, you can actually run an automatic parameter selection using the parameter sweep function we developed. So this talk today will be organized into 4 parts. Overview, and I will introduce some key design we have for Nimbus ML, and some benchmark results we have in the paper as well, and finally, the summary. So for many of you, I'm pretty sure you don't know ML.NET. So this is actually a work that originated from Microsoft Research since around 12 years ago. Back then, we were calling ourselves TLC. It's called the learning code. So if you ask the newer generation of the people at Microsoft, they don't know what TLC stands for. You need to ask older people like me. So this is a very long-term work that we keep adding a lot of state-of-art algorithm from MSR into this TLC package. So this package was always used internally within Microsoft in a lot of different applications in production within Microsoft. So eventually, I think 2 years ago, we decided we are going to open source this awesome machine learning package. So we kind of rewrite everything in C#, in C++, and open it up on GitHub and rename it to ML.NET. Now it can be used as a NuGet package in C#. And eventually, we also decide, since Python is very popular, especially among the group of people doing machine learning, so 2016, we decided to develop a Python wrapper around this awesome machine learning package. So here it comes, the Nimbus ML package. So it is very simple, a Python wrapper of this ML.NET package, and then we extend the Scikit-learn package in a very simple way that people can use it. So this ML.NET has been utilized within Microsoft by many applications like the chatbot and also this face logging. I don't know any of you use Windows, so you can open your Windows, switching on. If you have a camera, it will detect your face, this facial recognition. So ML.NET is not utilized in the image processing part, but it is utilized to determine whether it is a real person standing in front of the camera versus another bad guy holding your picture and putting in front of the camera. So this ML.NET is utilized as a classifier to detect whether this is a real face or not. And it's also utilized in email spam filtering to decide whether this is a real useful email or not. It's also utilized in the ranking model that Microsoft used to rank the search results of Bing. It's also utilized if you are using Excel. There's a little recommended chart icon there. So if you have some charts and you want to add some figures, there's a recommended chart. So this recommendation system is also developed based on this ML.NET application. So there are so many secret machine learning applications were developed within Microsoft that using this ML.NET. And now we are opening it up to the whole public. So there are three most important design goals of NimbusML. The first one is, like I mentioned, is Nimbus. We want it to be fast and accurate. So we claim that we do a lot of experiments using very famous data set that we can achieve 5 to 100 times faster than Scikit-learn. So imagine that if you are using Scikit-learn, you are using 30 hours to train a model. Now you are using 0.3 hours. That is just several minutes. And we are having so much good ML accuracy, especially if you are training a pipeline with default parameters. So within Microsoft, we maintain a very large experiment pool. We have millions of experiments in machine learning, so that over the past decade, we keep collecting those experimental data, and then we know that for what type of data set, what type of size of the file, what parameter usually works the best. So we fine-tune our default parameter for all of the machine learning package learners, and also follow a lot of state-of-art papers to update some of the parameters, so that in most of the majority of the case, you just go with the default setting, you can get very good accuracy out of NimbusML or ML.NET. We're also working on open up new scenarios, so there are so much effort on Onyx. It is an intermediate format of deep learning models. So if you heard of PyTorch, Caffe, or TensorFlow, all those deep learning models can be converted into Onyx. And then Microsoft developed this Onyx runtime together with Facebook, Amazon. So this Onyx format for deep learning model is now supported across a lot of different companies. And we can do the optimization all the way from the very lower level, from the chip side, to improve on the performance. So now this ML.NET, if you want to run deep learning models, you can convert that into Onyx, and you can call NimbusML to run that as a transform. We also support GPU through these Onyx models. So we have DNN. We can also support machine learning models like ranking. So traditional people think of a machine learning model are either classification models or regression models. So we opened up a third scenario, which is ranking model. I don't know anybody work with ranking before. So that is the problem that, for instance, I want to know we have a set of advertisements that we expose to different group of people, and people will give their perception about the ranking, about a subset of this advertisement. He will say, within these 3 advertisements, I rank it A, C, B. And for another customer, they will rank within this B, C, D, 3 advertisement. My ranking is D, C, B. So we collect this ranking that represent people's perception about a subset of the full choice. But our ultimate goal is we want to learn from all the advertisement from A, B, C, D, all the way through Z, what is the optimal ranking for all these advertisement among the whole population. So this is a type of ranking model that Microsoft is maintained within our production system. So imagine that for any search or advertisement recommendation system, there are this ranking model that is the key key algorithm that people will use. So we also support this ranking model for ML.NET and NimbusML. We also want that NimbusML can be always keeping up with the ML.NET. So what we do in our Python package is we create an automatic code generator. It's like AI writing code. So every time ML.NET adding a new function or adding a new learner, adding a new transform, we just rerun this autocode generator. It will add this new package or this new learner to NimbusML. So we can always keep updating NimbusML very fast, so we don't spend too much engineer hours to support this package. And the third one, which is also very important, is about the usability. So we want to expose this ML.NET as a Python API. We want it to be as easy to use as possible for all the users, and we want to support all sorts of various inputs. For instance, if you want to train the machine learning model with list, we allow it. You can train it with NumPy array, you can train it with pandas data frame, you can train it with pandas series, you can train it with I forgot, anything, usually, if you can play it with Scikit-learn also. We also allow people to actually mix up the element from Scikit-learn and NimbusML. So if you have a pipeline that you use Scikit-learn, you can simply swap it out. So I have some examples here. We have a kit. So hopefully this code is not so complicated for you. So I'm wondering, anybody used Scikit-learn before? Oh, actually, it's more than I thought. That's good. So for initiating or training a Scikit-learn package, what you need to do is to first initiate a pipeline. So in this situation, we are initiating a pipeline with 3 components. The first one is a count vectorizer. The second one is a TF-IDF transformer. So this is pretty much, we are dealing with a text scenario. So the first 2 are transform. That will transform, for instance, a paragraph of text into numeric values. And the third one is a SGD stochastic gradient descent classifier. That is a learner. So we chain them up, those 3 components. We have a pipeline. And then what we need to do is just do pipeline.feed with the training features, comma, the corresponding labels. And then when we want to make prediction about new data, what we need to do just pipeline.predict using the new features from the testing data, and then we will get the testing result. So this is a very standard Scikit-learn pipeline, and I hope it's a not very complicated one. It consists of 3 parts: initiating, training, and finally predicting. And then you might want to say, now I want to add some NimbusML flavor into here. What we need to do is just swap out 1 line. We can replace a Scikit-learn learner with NimbusML learner, which usually gets you much, much faster training speed. For instance, this fast linear binary classifier. So you can just swap it out and still do the model.feed, model.predict, and it will usually give you faster and better performance. And then if you want to switch everything into NimbusML, you can replace all the elements and use pipeline still, but you import the pipeline from NimbusML, and you do initiating, you do the training, you do the predicting. So this will be a fully NimbusML pipeline. And now I'm coming to very advanced usage of Nimbus, assuming that everybody is machine learning expert. You are the master of NimbusML. So here are a couple things I want to emphasize in our API design. The first one, you can see the first line. So usually, at least me, what I do in Python is I will read the original data from CSV using pandas, like pd.readCSV. Or anyway, you load the data into memory. But in NimbusML, you can do the same thing. Yes, we support pandas data frame as well, but we also support something called fire data stream. So you can create a fire data stream just using fire data stream.readCSV, you input your data.csv. What this line does is it creates a pointer, point out to your data set. Instead of imagine now you have a 1 terabyte, 10 terabyte of data that doesn't fit into memory. What you need to do is just create this little pointer, point to your data set. And then you can use this pointer in the training process, which I will discuss the benefits later on. So you can train a model with Fire data stream as well. And in the pipeline, you can specify, for instance, we have this n-gram featureizer to do the text natural language processing part to convert the text into numeric values. You can specify what are the columns you want to use from the original CSV file. For instance, in this file, maybe I have a column named in. So in the n-gram featureizer, we introduce this quack. I don't really like this quack in Python, but you can also specify within the quote bracket saying columns equals to in, so that it will specify you what are the columns you want to use for this learner. So imagine that you can specify the input for this transform, the name of the column, which is in. You can also specify after this transform, I want the output column to be renamed to out. And then same thing for the second learner, you can specify what are the columns you want to use as the feature for this learner, and what are the column you want to use as label. So imagine that it's very, very similar to the TensorFlow or deep learning package. You are imagining that you are adding layers after layers and stack them up and chain all the learners, transform up. And for each learner, you specify what are the input, what are the output. And for the next learner, you can select a subset of the column from the previous learner or all the way from the raw data, and then use that as input. And you can rename it to another name as the output, and you kind of stack up. And this will allow you to create a very, very complicated pipeline. And this is my very favorite function of NimbusML. It is called img_export_pipeline. So if you create a pipeline like we have in the previous page, what you need to do is just put them into this bracket. It will visualize the pipeline you just created. So I hope I can hide this. But this figure at the very top level, you can see is maybe 12 columns. That is the column name from the very raw data. We have a country, description, designation points, price, and then we add around 9 transforms. And each transform, you can see they are using different columns as input, and it will spit out quite a few different other columns. And for each one of the transform, you can specify what columns you want to use as input, what columns you want to rename it as output. And then the yellow one, which is the light GBM regressor, I highly recommend this learner for everyone, both the regressor and classifier, because it is proved in industry. It usually achieve very good performance, not only in speed, but also in accuracy as well. So in this light GBM regressor, we can see that we are using around 10 or 20 columns as the feature. And also we have one column to be used as the label. So we also allow the scenario that if you want to have different weights for the different sample, you can have another column in the original file to indicate how much weight you want to put on each individual observation. And then when you are training the pipeline, when you initialize this light GBM regressor, you can specify a row which is called weight column. Is this the name of the corresponding column from the original data? And then that will complete the full pipeline to help you do the training and feed. And this is a code sample from the previous situation that we initialize 1 to 6 components, 5 transform, and 1 learner. So after this quack, the list of string indicating what are the columns we want to use for each one of the transforms. And you can also see that for the light GBM regressor, we actually specify the rows of different columns. For instance, feature, our country, province, region 1, variety, description, points, and also the label column is the price column. So this pipeline, we are trying to make a prediction about how much a bottle of wine is based on where it is originated, which country, which province, how much points. Points, I think it's some expert giving some scores of the wine. So we can make prediction using a regressor. And then the model equals to pipeline, we are just chaining up all the learners and transform together, and they will know from the order as well as the input-output columns to know which column they need to grab from the previous data, and then we can do the model.fit. So coming to the architecture of Nimbus ML, it's actually relatively simple for a data scientist like me, because we don't work on the most complicated part, which is the core part of ML.NET. So what we have is one side on the Nimbus ML, we have this public API in Python. Like you see, we can initialize the learners, we can do the feed, the predict, we can do the test, and what we have is to use the entry point API from ML.NET that to construct how the computation graph will look like. So we standardize the pipeline into a JSON file that has all the information about the name of the components you are using, the input and output column of that component, and also the corresponding schema or the data structure of the input-output of each component. And we pass by this entry point JSON file to the ML.NET from the Python side. And for the developer on the Python side, what we need to do is to translate what users specify in Python code into this JSON file format and pass it by to ML.NET. And the rest part is the communication of data input-output between the Python side and the ML.NET. I won't go to detail. But there are two key designs I want to emphasize. The first one is we use data view. It is a very important concept in database. I'm not so familiar with that though, but the key thing I want to emphasize is imagine that on the right-hand side of the code, we are not actually passing by every information in memory between the learners, between the transformers, or between the feed, between the .NET. We are actually passing by a view only. This view, we specify all the operators we will use. So we are not loading the whole data set into memory, but we are doing a lazy evaluation. That means when I'm super lazy, I hold on everything to the very end, the very last step, unless I have to materialize some of the columns. So imagine that in the original data, you might have thousands of columns, but when you're creating this data pipeline, you are actually only using maybe 100 of them or 20% of them. So using this lazy evaluation, we will only extract the data or materialize the data when it is needed. So this helps us save a lot of memory in the training process. This is not mostly not the data science concern, but what we can see is if you look at the CPU usage or look at the memory usage, you can actually save a lot of memory for the pipeline training. And the second thing is about the streaming data. Like I mentioned, if instead you can train with a pandas data frame, NumPy array, yes. But I also highly recommend you to train it with streaming data, like the fire data stream I just mentioned. So in that case, if you are training with 2 terabytes of data, no problem, go ahead. The data will, the pipeline from NimbusML will create a cursor from the original data and grab the data on the go when you are calling the pipeline.feed function. And then also, it allows for parallel computation. So in some of the algorithm, if it allows for parallel computation, it will generate multiple cursor from multiple parts of the data set, and everybody start grabbing the data from multiple places so that to allow you to reach 1248 times speed up. So if you can also specify how many cores you want to use, you can use 1, 2, 4, 8, 16 if you have multi-cores in your computer, and you can see significant performance improvement if you have more cores in the laptop. So this will help you to speed up the training process very well. So I have a couple minutes. So what we have is a very detailed experiment in the paper. We tried it with Criteo dataset. We tried it with Amazon dataset. We tried it with flight delay dataset. Usually it's a relatively large dataset. So you can see that we compare the performance with ML.NET. We tried with Nimbus ML training with data frame, pandas data frame. We tried it with Nimbus ML training with the Fire data stream I just mentioned. We also tried the H2O machine learning package. We also try with Scikit-learn. So you can see that for H2O and Scikit-learn, they all run out of memory error if we are training with the full data set of Amazon, if we are training with 100% of the data set. So the x-axis is how much data I'm using. Is a 0.1% of the full data set, 1%. So you can see both H2O and Scikit-learn doesn't have a value there. That means they are out of memory. But still, Nimbus ML, ML.NET can still achieve very good accuracy as well as very fast runtime. And the y-axis for the runtime is actually log scaled. So if you see they are slightly away from each other, they are actually, it's 10 times faster. So we proved that we can expose a very fast, battle-tested state-of-art ML toolkit and allowed users to train a machine learning model using out-of-memory streaming data to achieve the best performance. And we have documentation sites ready. You can search for all the learners we have, and everything is open source. That means you can search for Nimbus ML, you should be able to see the GitHub. We also have quite a few notebooks, tutorials, either on YouTube or on GitHub to show you how to use Nimbus ML in different scenarios. Yeah, thank you.
We have a little bit of time for questions. I'll try to run the mic over.
Hi, thanks. Great talk. So is there any pre-trained models that come with Nimbus? For example, MATLAB has this program called AlexNet, and it has image recognition right out of the box. Does Nimbus have anything like that?
Yeah, so one thing I want to emphasize is we are pushing a lot of effort in this Onyx model. So Onyx model, imagine that you can have all the deep learning model available, like ResNet 50, ResNet 100, VGG16, VGG20. You can convert all those deep learning models into Onyx. And then those deep learning models can be used to featureize the images you have. So it's kind of served as the transfer learning. But as our team, we don't focus on this part, but you can definitely download those models that people created on GitHub in PyTorch Cafe, and then convert that into Onyx model. And then in our Nimbus ML, you can actually initiate an Onyx transformer, and you specify the path to your Onyx model. And then they will use this as a transformer into the pipeline to do the transfer learning, to do the visualization of image for you.
So great talk. Thank you so much. I really love Nimbus ML, particularly how you worked with like addressing particular columns. It's so great that actually Scikit-learn basically stole LightGBM, and the next talk in here will be about how Scikit-learn is now about as fast. So basically, we looked at your graph and said, oh my God, this is terrible. And so now we're doing the same thing that Nimbus ML is doing. So, great work.
Thank you, thank you. Yeah, I think one of the key things, at least from my point of view, of Nimbus ML is actually a concept. You can train the model directly from the file name. You can imagine that you use the pointer. So even though that we are using the same algorithm, ML.NET or Nimbus ML still have some advantage in terms of speed over Scikit-learn. But we are good friends with the developer of Scikit-learn. We get a lot of feedback from him about the documentation, about the API design from Andy. Yeah. Oh, I see. I should have better prescription for my courses now. Yeah.
Any further questions? All right, let's thank Ewan again.
Thank you.